Hi everyone, thanks for tuning in. My name is Blake Duschatko and I'm a PhD student at the Harvard School of Engineering and Applied Sciences. Today I'm going to be talking to you about some recent work that I've been doing on understanding how Gaussian process regression can be used for designing better coarse grain potentials. So what is coarse graining? Our goal is always to understand something about how a system behaves, whether it be its structural properties, thermodynamic properties, or even its dynamics. But if we start with some all-atom system, it could be that the length scales and the time scales that we're interested in are just too expensive to simulate. In this case, the first problem that we're interested in solving when we do coarse graining is how can we remove degrees of freedom? Usually this involves deciding how to group atoms into composite units, or beads, such that we remove especially fast degrees of freedom. Once we do this, we need to figure out how to describe the interactions between these units in a way that will give us the properties that we're interested in. The third problem that may or may not be important, depending on the application, is that of reconstruction. That is, how do we go from our coarse grain representation back to our all-atom representation? I'll focus today's talk on the second one of these problems. To give you an idea of where coarse grain forces typically come from, we can lay out various methodologies in terms of their sophistication. On the lower end of this spectrum are simple parametric models, often involving things like simple Lennard-Jones or harmonic type terms, and these are quite fast but rather limited. Such models might be fit to things like statistical regularities and protein conformations, for example. Increasing in complexity, we may have similar parametric models that are instead fit to experimental observations, and a good example of such force fields are the Martini force field. Moving along this progression, our goal might be to fit the radial distribution functions of a system. These approaches typically use more complex, non-parametric methods such as spline models. Then at the highest end in complexity is the potential of mean force, and it is here that machine learning methods have most strongly come into play. But what is the potential of mean force? The central idea goes as follows. Let's take butane as an example. If we start with some orientation of the carbon atoms and choose an all-atom to coarse-grained mapping that preserves the carbon sites and integrates out the hydrogen degrees of freedom, then we should note that any conformation of the hydrogen atoms with the carbon atoms fixed will have the same coarse-grained mapping. We define coarse-grained consistency as the requirement that the configuration of carbon sites be sampled in our coarse-grained molecular dynamics trajectory with the same frequency as the sum of probabilities of all equivalent all-atom configurations. The resulting force on the carbon sites in the coarse-grained picture then takes a simple form of an ensemble average of their forces for all the different all-atom configurations with the same mapping. The key ingredient to all of this, and the reason for choosing this approach, is that this method preserves all thermodynamic properties of the all-atom system. A great deal of progress has been made in designing machine learning potentials for coarse-grained applications in recent years. A majority of these approaches have been with neural network potentials, with little emphasis placed on the appealing properties of Bayesian methods. For one, a Bayesian framework allows us to directly probe the complexity of the coarse-grained potential without the need for large training sets or held-out test sets. Instead, we can use the interpretability of Gaussian processes to analyze complexity on small training sets alone. This is essential in designing potentials that give an optimal performance and efficiency trade-off. Moreover, while active learning schemes have been successful on coarse-grained water systems, this has not been done with principled uncertainty quantification. In the present work, we will address both of these challenges. As a kernel-based machine learning method, Gaussian process regression requires us to define a similarity metric between inputs to make predictions. To this end, we consider the atomic environment of our coarse-grained sites and compare the distances between pairs and triplets within two sets of cutoffs. These kernels give covariant and symmetry-preserving force fields, and they have the added benefit of having interpretable hyperparameters. By making predictions with a Gaussian process, we'll further have access to predictive variances that will enable principled active learning. Let's start by examining the benefit of interpretability that is enabled by Gaussian processes. For this example, we consider reducing liquid methane, ethane, and propane to just their carbon sites. The noise hyperparameter of our model gives us an indication of both the noise inherent to the data itself as well as that inherent to the model. That is, it tells us to what degree the model is incapable of explaining the data that it sees. In this plot, we consider models that have been passively trained on a fixed training set and observe how the noise behaves as we change between two-body interactions and both two- and three-body interactions. We also examine the behavior as a function of ensemble sampling of the coarse-grained force labels. It's clear that the noise indicates, in line with our intuition, that three-body interactions become increasingly important for more complex test systems. But how does our new understanding of the potential complexity help us in designing potentials in the first place? These plots indicate that we should expect the addition of a three-body kernel to have the largest effect on the performance of propane, with very little effect on methane. To see that this is the case, let's turn our attention to our on-the-fly active learning protocol that will enable us to run simulations with our coarse-grained potentials as we learn them. We can then compare the performance of our potential on things like radial distribution functions to see if using the Gaussian process noise as a complexity probe is a good idea. In this framework, we start with a constrained dynamics run of an all-atom simulation. From the previous plots, the noise should indicate to us how much sampling will be sufficient. Then, we can coarse-grain this information and collect the average forces to use as training data. The hyperparameters of our model are updated in the training stage, and the Gaussian process is used to make predictions of forces on a coarse-grained site and take a molecular dynamics step. If the predictive variance is too high, we can reconstruct the all-atom information, perform constrained energy minimization on the fine-grained degrees of freedom to avoid unphysical all-atom structures, and repeat the loop as necessary. When the Gaussian process is confident in its predictions, it will continue on with the simulation without needing to reference the all-atom baseline. When we do an on-the-fly simulation of our coarse-grained methane model, we can indeed see that the 2 and 2 plus 3 body models replicate the all-atom radial distribution function between carbon sites very well. As expected, there's little difference between the performance of either of these models, as can be seen in the root mean square errors of the RDFs. We note also that their mean absolute errors are both quite small at around 10 MeV per angstrom. Similarly, we can look at the performance on our ethane system. In this case, we consider two different two-body models, one with a 4.5 angstrom cutoff and the other with a 6 angstrom cutoff. While the model with the smaller cutoff is unable to capture the second coordination peak, the one with the larger cutoff is. On the other hand, the 2 plus 3 body model, which has small 4.5 angstrom cutoffs for both the 2 and 3 body terms, is able to capture this structure without the need for larger cutoffs. The mean absolute error between these models and the all-atom baseline are comparable, with a small improvement in the 2 plus 3 body case. It is here that we begin to see the utility of Gaussian processes as a complexity probe. The noise hyperparameter for ethane indicated that we should expect only a small variation in the performance of 2 and 2 plus 3 body models. Because the computational complexity of the 3-body kernel is much higher than the 2-body kernel, in a practical setting, we might decide that we're happy to just use the 2-body term for its computational efficiency. Finally, we can examine the performance of our on-the-fly routine for coarse-grained propane. Here, the 1, 2, and 3 labels are understood as the first, second, and third carbon sites along the propane chain. Perhaps unsurprisingly, as indicated by the noise plot we saw earlier, a two-body model is completely incapable of capturing the correct physics of the all-atom system, with extremely large mean absolute errors around 200 MeV per angstrom. For clarity of the plots, we haven't shown these radial distribution functions here. We can, however, see that the 2 plus 3 body model is quite capable of capturing the salient features of the all-atom system. Here, the mean absolute error of the model sits around 75 MeV per angstrom. We note that the artifacts in some of the plots may be a result of the need for a more many-body potential, as it is often the case that coarse-grained potentials quickly become many-body upon integrating out degrees of freedom. In summary, we have successfully demonstrated the following things. For one, Gaussian processes can probe the complexity of coarse-grained potentials without the need of a test set. Secondly, active learning with uncertainty can be used to construct accurate coarse-grained potentials capable of capturing things like the radial distribution functions of the all-atom system. The combination of these will help in the performance and efficiency trade-off of designing coarse-grained potentials in the future. I'd like to take a moment to acknowledge those who have contributed to this work. In particular, I would like to thank Jonathan Vandermoss, Dr. Nicola Molinari, as well as my advisor, Professor Boris Kaczynski. I would also like to acknowledge the computational resources provided by Harvard Research Computing and NERSC, as well as funding from a NASA Graduate Student Fellowship. Thank you again for listening, and please feel free to contact me with any questions you might have.